Hi, I'm Rob Carlson. You've heard some of what I had planned to say already, so I can skip through some of my slides. The first thing I want to say is we've been engineering biology for a long time, one way or another. These are living bridges in northern India, composed of more than one plant type. They take maybe decades to grow. They're around for centuries. But it's a really slow design and manufacturing process. We can't really use that kind of growth and training of biological systems for the rest of our economy. So that's where synthetic biology comes in. So for the purposes of this talk, synthetic biology means engineering of biological systems. In other environments, you might hear people talk about synthetic biology as being origins of life, or other kinds of applications. What I mean is using biological pieces to build new things. But before we get there, we need to take a step backwards and imagine how we got where we are today with all the rest of the things that we build. So let's say it's 1892, a century before the 777 takes flight, and you're presented with a 777. Right? So the physics is the same. No, physics hasn't changed. But all of a sudden, you have this massive beast. It eats brimstone. It breathes fire. Basically, it's a fire-breathing dragon. It can carry heavy loads. You don't understand the materials. You don't understand the systems that fly it. Robots fly this thing 90% of the time. Humans don't touch the controls. And then somehow, over the course of a century, we go from not having any ability to do this at all to being able to assemble this from parts, all of which we understand individually, into systems that we understand individually, into airplanes, and effectively you design the 777 on a computer and hit print, and it comes out of a big printer in Everett, Washington. Yes, there are people inside there as well as robots, but that's a manufacturing system that's developed to be a really sophisticated way to produce stuff. We cannot yet do that with biology, but that's where we're going to go. And the way we get there, just like with automobiles, is we have lots of automation coming online today to facilitate doing not just biological experimentation, but process development. So if we're going to make stuff out of biology, we need manufacturing processes to go with the organisms that we build, and that's how it's all going to come together, just like it does for cars. And so I'm actually going to skip through some of this stuff because we've heard it already. So they're the latest version of the curves. You know, productivity is going up, cost is coming down. That's the fundamental reason why we're able to read and write DNA so effectively today. I'm not going to advertise a lot about the investment fund that I run, but one of the things I wanted to say is that if you look at the tool stack that allows us to do mechanical engineering or to make chips, it starts with software that you use on a desktop or a laptop. It allows you to do layout, testing, design, talks to other software that eventually talks to a robot that makes whatever it is you're trying to make. Again, we don't have that for biology, but my job in running my fund is to build that infrastructure. So we invest in companies, starting with Arzeta, Zymergen, et cetera, who can do layout, down through companies that are building software to wrangle robots and enable statistical analysis and statistical design of new systems, all the way through to Lumen, which is a manufacturing company. I'm going to just skip ahead through some of this stuff, I think, in the interest of time. One of the things that we can talk about later as we get into the discussion is that biotechnology is actually much larger as an industry than people understand. And the technical reason, is that we don't measure it. So whereas in 1958, when semiconductors became a thing in the United States, were less than 0.1% of the economy, the government was already tracking how big that was in the economy, how many people worked in that industry, and it's been measured very well ever since. So now, as of 2012, biotechnology in the United States is more than 2% of GDP, more than $325 billion a year in revenues. There's no official tracking of this industry, so nobody really knows how big it is. This data comes out of a paper I published last year in Nature Biotechnology, and you can dig into that if you like, or we can talk about it later in the session. And the one thing that I want to point out on this slide before I go on is that we already are producing large amounts of chemicals using biotechnology that are displacing petroleum from the marketplace. This is a huge industry, and it's already transforming the economy. And just briefly to let you know that the change in this industry is very rapid. In 1980, we had no revenues from biotechnology. That's when the industry got started. And we're seeing this rapid increase over time, and that's only going to continue. We'll see revenues from genetically modified crops maybe come down a bit, go up again, come down a bit, because that's the way commodities work. But overall revenues are just going to keep climbing because the demand is there, the pull is there. So where are we going to get all our stuff in the world? Let's say we want to dial down petroleum and use biology instead. Well, the main place to look to understand where this is going to come from is in this middle blue band in terms of the composition of a barrel of petroleum. So a barrel of petroleum is not a homogeneous thing. 85% of the volume of a barrel of petroleum is only 15% of the value. That's gas, diesel, or tar, so we burn it or we put it on our roads. The other 15% of the volume of a barrel of oil is 85% of the value. And that goes into all the chemicals that we build our world out of. This room is full of petroleum products one way or another. You're probably wearing petroleum. You eat petroleum one way or another. Even though we're trying to get that out of our food supply chains, it's there anyway. And biology can make every single molecule in that blue band in real time. There's about 7,000 different molecules that are pulled out of there and put on the market. We already know how to engineer biological systems, microbes primarily, to make each one of those things. And over time, we will displace petroleum and outcompete it using biological manufacturing. And then just to finish up, I wanted to bring this back to the context of the auto show and our sponsors with Mercedes-Benz to think about what parts of the car of tomorrow will be grown rather than pulled out of a hole in the ground. And some of that's already available today. So starting down there on the right, we heard about Amyris already. Amyris is producing an additive for tire sidewalls that stiffens up the tires and increases fuel efficiency by 10%. So that's not making biofuels directly, but it is a significant impact in the efficiency of the car. We're going to get leather that's cultured in vats and used for car seats rather than removed from animals. We're going to get other kinds of materials, whether it's the windshield or even the batteries, where the electrodes are grown using viruses as templates. So the future, in essence, is about what we can learn to grow, learn to design with biology, and less about pulling it out of a hole in the ground. And I'll just leave it there.